All right, so maybe we can get started. Welcome everybody. So this is our second seminar in our summer series of the International AGN Seminar. So I see a few people who weren't here last week, and so I'll just say briefly that this idea came up after we had been, a few of us AGN enthusiasts had been meeting for the course of about a year to talk about potential projects to do with very high resolution, diffraction limited spectroscopy and imaging with KEGG, with a potential future project called ORCAS. You can ask us more about it later. But we thought it would be a good idea to keep the momentum and keep these discussions going. So Shabita actually had the idea of having this seminar series during the summer. And so I'm co-hosting with her. And today we have the pleasure to have Stephanie Juneau talk to us. So I'd like to introduce Stephanie. Stephanie graduated from the University of Arizona with a PhD working with Mark Dickinson. And after that, she went on to Marie Curie postdoctoral fellowship at Saclay in France, where she stayed on to be a staff researcher for a while. Stephanie, I have to say, is one of the most enthusiastic AGN astronomers that I know, because I see her in every single meeting that I go to and every collaboration. And I'm like, oh my gosh, you do that too? Like, she does everything. So I wasn't surprised that she was at ORCAS too. She has many, many talents. So anyways, a few years ago, she came back to the US, and she is now a staff researcher at the Noir lab, which I wasn't exactly sure how to say, but now she's let me know. So anyways, I'm very excited to introduce her. And Stephanie, you can take it from here. So thank you for coming.
Great, thanks. I was not expecting to be blushing during the introduction, but thanks, Gabby. Hi, everyone. So I'm happy to be here. Let me go ahead and share my screen. All right, and go in full screen. Okay, so I hope you're all holding up okay during these times. So I'm going to be talking about kind of two topics, all related to AGN, of course. So AGN feedback, what we can learn from zooming in, and I'll mostly spend time on one case study because it's a thing I've been working on for a few years that I'm excited about, but there's a lot of similar and other studies in the literature as well. And also I'm going to talk about what can we do, kind of looking toward the future. How can we leverage very large upcoming galaxy surveys where we have millions and millions of objects to choose from to study and answer these questions? So maybe I'm preaching to the choir here, but let's just still all get on the same page, in particular our students in the audience. So there's a lot of, well, at least a few different reasons why we think that supermassive black holes are closely linked with their host galaxies. So one of them is the famous M-sigma relation. So there's a proportionality between the mass of the black hole and the velocity dispersion of the galaxy bulge. And sometimes this is shown also in terms of the galaxy mass. But there seem to be, in any case, some relationship. So the bigger the black hole, the bigger the galaxy in some sense. So, overly simplified. So why is that? Is that a physical connection? When we look at black holes and the galaxies as a whole, as a population, and if we trace their history of growth, so starting at early times at high redshift, all the way to now, the present epoch, we see that they both have a very similar shape in their growth history. So growth history is really the growth per unit volume in volumes of the universe. So all galaxies together, all black holes together, we're growing with a rise in accretion rate and a peak at what is sometimes called cosmic noon, and then a sharp decline. So it seems that even though we don't know for sure that every galaxy and every black hole is really growing in tandem, as a population, galaxies and their central black holes are growing together. And another reason, which is actually what I'll be focusing most on this talk, is there seems to be a need, at least in simulations, to have a form of AGN feedback to regulate the growth of galaxies, and possibly self-regulate, so regulate the growth of black holes themselves. So the question of AGN feedback has been around for quite some time. And it's not an easy one to answer, which is why we're still all interested in talking about it. What we do know is that there's plenty of energy. So if we were to calculate the energy budget, how much energy is produced, so either in the form of a radio jet, which can come out of the galaxy and dump a lot of heat in halos and reaching very large scales. There's a lot of energy there, but also this more radiative feedback, which is the disk around the black hole, the disk wind, the radiation can apply radiation pressure and push the material, and we end up with these kind of fast winds that can reach over thousands of kilometers per second. So both of these phenomena are very different in physical origin, and yet they can influence the surrounding. So the disk might push a material in the galaxy. This can shock, heat, or remove the material, so the gas that is needed to form stars. And similarly, the radio jet can reach even further out. And then I'm going to talk about a bit what could be very interesting with also the maybe more neglected small radio jet that are low power, but that can still have a big impact on host galaxies. So what we also have been finding is a lot of observational evidence that outflows exist. So outflows are winds that are produced, we think by these accretion disks, but it's different ways. But what we know is that we can find the outflows for sure. So if we can find them in molecular gas, ionized gas, neutral gas, this still doesn't mean that we fully understand feedback, because they could be an outflow while the galaxy is still happily forming stars or accreting new gas at the same time. So the question of feedback depends a lot, might depend also on the coupling. So we know there's plenty of energy, but is the energy actually applied or coupled to the gas to move it or remove it or heat it up? So I want to start here by looking at this effort from the numerical simulation side, because it's a little bit of a motivation for the study that will come next that I will talk about. So what I'm showing here is a simulation of a gas-rich disk galaxy. So it's one single object, like an isolated galaxy. But the simulation was done with this adaptive mesh refinement technique, which means that the denser region have finer resolution and the diffuse region have a coarser resolution. And the simulation itself has a black hole already in this galaxy. And there's a form of thermal feedback, which is the simulation keeps track of how much material comes in a small region around the black hole. And then when there's enough of that material, it dumps the thermal energy. So it will heat the surrounding cells in a simulation around the black hole. And this thermal feedback would create winds. And then a few years back, with a graduate student, Oriane Rose, in France, when I was there. So Oriane led the effort to add photoionization from an AGN using cloudy and propagating along different lines of sight, so through the galaxy and away. So it's hard. So the picture here is actually from the simulation in 3D, and you can see the gas density. So this diffuse kind of halo gas, and then there's a very clumpy gas-rich galaxy here. So the result of the photoionization, where we wanted to demonstrate how far the AGN photoionization will travel as a way to probe how much of an impact it will have on a galaxy. So if you just look at the top row for now, on the left-hand side, what you can see, if you can see my cursor here, this is a side edge-on or sideways view of the galaxy. So this is a density map. So dense gas here in the disk and very diffuse in the halo. You might notice already a denser clump. This was from a previous feedback, AGN feedback episode that pushed the gas here. But this is the disk of the galaxy. And then what we did, these three panels are three increasingly higher AGN luminosity. And then with cloudy, we say how far is the gas ionized and how much is it ionized? So if it's black, it means that it doesn't see any of the AGN radiation. It just recombines, it doesn't reach there. So and also we did not put in a torus, right? So this is AGN radiating in all possible direction, like full 4-pi steradian. And what you can see is from left to right, from lower to higher luminosity. So there's already cones that are forming. They're big, right? They're very quite open. But these are cones coming from the galaxy. They're not coming from a torus. And these ionization cones get even wider with the more and more luminous AGN, also as expected. Even in the most luminous case, which would be a luminous quasar, we see that the disk, because it's clumpy, it's actually kind of protected. So the galaxy is protecting itself against the AGN radiation, even if there's no torus in this simulation here. So to us, this indicates that the substructure or the shape of the ISM actually plays a role in how much the feedback of the AGN can affect the host galaxy. So this is from a simulation where we would just add the AGN at different snapshots. So at the bottom, we're kind of showing what happens if you just have kind of very random typical snapshot, which is the same one that's shown above actually. But then this is a strongly embedded snapshot. So this is a case where by chance, this galaxy is quite clumpy in the ISM. There was a clump of gas that just went around the center at that time. And so you can see that even with a quasar, it's actually struggling to, the photoionization is struggling to get through here. So again, this will emphasize the case that in terms of what we see for the signature of AGN and possibly the feedback from photoionization might strongly depend on the galaxy's substructure around the black hole. And all this, when this was happening, there were fast outflows, and the outflow rates were similar to the star formation rate of the galaxy, so the order of 20 to 30 stellar masses per year, but the star formation rate would not get reduced. So the galaxy still keeps forming stars, even though there's also outflows. So there's no immediate quenching that we could see, so even though, despite the presence of these outflows. So now I'm gonna go to an observational study motivated by this. So I'm gonna talk today mostly about this galaxy NGC 7582, which is part of the Gruis Quartet. So you can see 3 of the quartet here, and the 4th member is in the basement right now, so we don't see it. It's a bit further away. So there's these 4 galaxies, but really I'll be focusing on this one, others at the top. So this is work that I think I've mentioned. This has been a long-going project. So there's many collaborators from different countries. That should be a very fun learning experience because there's radio astronomy experts, X-ray astronomy expert. Like we have all this nice different group here. So what do we know about this galaxy? Why did we choose it? So it's heavily obscured in X-rays. It's actually sometimes Compton thick, sometimes Compton thin. So it's like borderline. So it's not always like a true Compton thick AGN, but it is heavily obscured, and there's some short time variability. So there's some very dense gas, very small scales, like within the broad-eyed region of the AGN. It looks like a type 1 in the infrared, but it's a type 2 in the optical. So this is a bit unusual. What it indicates most likely is that there's a presence of a larger scale kind of dust screen. So it's not just a torus doing the obscuration. There was already existing 3D spectroscopy before from the S7 survey, but in a smaller field of view and also lower resolution. So we wanted to really take a closer look, which is why we applied to use MUSE on the VLT to look at this object. So MUSE, I think some of you may be familiar, but just as a reminder here, it's 24 integral field units, and you can see here the kind of resolution it has. So it's in the optical, and very nice. It has a field of view of 1 by 1 arc minute, and it's using an image slicer to cut the field of view basically and take spectra, and there's 300 by 300 roughly spexels. So it means that there's 90,000 spectra for 1 cube just on the field of view here. So this is this NGC 7582. You can see the background is that picture from before, and then this is a MUSE field of view where I simply took the 3 different bands to do red, green, blue to create a color image. We can see that we find from the MUSE cube, we recover the dust lanes, and also the fact that it's highly reddened in the center, so lots of dust, but also something very bright in there. So there's already previous results that showed there's a starburst also in the center of this galaxy, just to complicate things. So there's an AGN and a starburst around it, and then there's all these like very nice dust lanes. Oh yeah, and also there's a bar in this galaxy here, and that also influences what we see in the kinematics. So from the MUSE cube, we can learn a lot because since we have spectra everywhere, we can make slices just to look at certain emission lines, or we can, which is what I'm showing now, and then later I'm also going to show you with the spectra, we can look at the kinematics. So we have the stellar continuum, so we can learn about the stellar kinematics there, and we can use the emission lines to look and their line profile and their shift and their width to look at gas kinematics. So in terms of the ionized gas, if you look on the left side is an H alpha emission line. So this will trace the bulk of the ionized gas in the galaxy here. And what you can see is this trend where along the disk of the galaxy, we see a lot of these kind of denser, brighter clumps. So these are most likely, star forming along the galaxy disk and bar. And then there's a blob in the center here where we have a starburst and an AGN together. Which is more striking, so this galaxy has a high metallicity. So this is typical, not super high mass, but massive enough galaxy at low redshift that typically there's a high metallicity, which means that the O3 emission line is actually weak in star forming gas, but it will be strong if there's an AGN ionizing it. So if we look at just the O3 emission line, which is on the right-hand side here, you can actually already see by eye this shape like a cone. And then you can see this other one, which is the back or counter cone behind the galaxy. So we're already seeing these AGN photoionized cone in just looking at O3 without doing much analysis. But now I'll show you afterwards. We'll dig it into some more details. So I want to show visually first, and then I'll show you more of the measurements. So visually, this is the image I was already showing before. And if we add the O3, my motivation to do this is I want you to observe how we can get a sense of the ionization coming out of the front cone and also the back cone. It's nice to see that we actually see it between the dust lanes. Oops, sorry, wrong way. Okay, so I'm kind of going back and forth a few times to get everyone a chance to see that. And no matter how many times I've done this, I never get tired of it. And I'm always like, ooh, look at that. Okay, so the interpretation is that we have this biconical outflow. But to know it's an outflow, we need to know that gas is moving. So we'll look into the kinematics next. So for the kinematics, I'm going to also show what the stars are doing and what the gas is doing. And it turns out for the gas, we have two different components. So what I'm showing on this first slide here is on the left-hand side at the top, you can see the gas kinematics. And then on the right-hand side, sorry, the stellar kinematics, so the stars. And then on the right-hand side is the first component of the gas, which is the bulk of the gas in the disk of the galaxy. So these two are actually quite similar to each other. So the main thing is a very large scale rotation, right? Blue shifted and red shifted. So the whole galaxy is rotating. So blue shifting toward us and red away from us here. And then this is similar. If we, again, stick to the larger scale, there's some variation in the gas that maybe we can see a trace of having the bar, this kind of streaming motion. That's a bit, maybe it's harder to see, but there's a faint yellow at the top and faint cyan kind of line. And these are going basically along the leading edge of the bar. What is also interesting, if we zoom in the stellar kinematics, if you look at these two spots in the center here, there's a rotation in the same direction as the galaxy, but it's faster. So if you see, this is a red spot and darker blue spot, those have enhanced velocity compared to the surrounding. So this is a KDC, so a kinematically distinct core, which I'm spelling out here, and it's co-rotating with a galaxy. And such a core could be a disk or a ring, and we always suspected it was a ring, and I'm 100% sure like if we could quite demonstrate it before, but something that came up very recently in the literature and that I got really excited about is that the ring is actually resolved with ALMA, but ALMA sees the molecular gas. So this is CO221, which you can see on the right-hand side, and it's over this small region here. And clearly, at least ALMA shows that there's a ring, at least in the molecular gas. So this gives us a little bit more confidence in our interpretation, which started as a guess, a bit more of a guess, but now it's let's say more of an educated guess. So this is nice, and it's not unique. Other objects. So I'm going to be talking mostly about this one case, but I want to say that as I started working on this and looking at literature, there's more and more of these cases that are being found. Okay, so now let's look at the second component of the gas. And what you can see here, so I'm adding this on the third panel on the right. And blue shift, the front cone is very much blue shifted, and the back cone behind the galaxy is red shifted. So this confirms the suspicion that there's actually an outflow. And these are the projected velocities along the line of sight, reaching a few hundred kilometers per second. So we have this outflowing ionized cone, and then the bottom is again a reminder of this ionized, doubly ionized oxygen. So this is telling us that there's some outflow. But I already mentioned, so we know there's a ring, and we see the ring in molecular gas, but also there's some starburst going on in this ring. So is there outflow coming from the starburst or coming from the AGN? This is definitely a valid question. So in order for the outflow to be causing AGN feedback, it needs to come from the AGN and not from the starburst, obviously. So one thing we're gonna look at next is to see, can we see the ionized properties of this gas to tell if it's ionized by AGN or ionized by starburst. So I'll be showing two emission line diagnostic diagrams. One is the BPT, and the BPT is two pairs of emission line ratios, and they're closely separated to each other, so they're not so sensitive to dust. And normally, if we look, so this is 1 point per galaxy from Sloan. There's a star-forming branch of galaxies, and then an AGN kind of distinct branch with this composite region in between with some kind of blend. Roughly, these line ratios are very sensitive to the ionization parameter. So number of ionizing photons per atom of hydrogen, and gas phase chemical abundance, but it's actually more complex than this. They're not truly independent. If you look at photonization models and grids, they kind of fold into space here. So this is just kind of some rough guidance to understand. So the top row is showing the same BPT diagram I was just showing, but now each point on here, which is like a distribution, but comes from one spaxel in the galaxy. And indeed, I'm using this to color code them in blue, green, red, and then I'm showing them back on the map of the MUSE data. So you can see that this red AGN region is where the cones are mostly having these AGN emission line ratios from the BPT. And then these denser, the blue spots here are these kind of denser star forming regions. And then this green goes to be in between here. So which could be some diffuse gas. It could be what we call the WIM, which is the warm hot ISM, that's on the medium. So, and then on the right-hand side is the same map, except it's flux weighted. So where there's more flux, it's more white, and it's black where there's less flux. And then the bottom, so this BPT is nice because it's quite sensitive. So the composite signature would be sensitive to anything that's non-stellar. It could be AGN, it could be shock, but it's quite sensitive. But shock and AGN kind of are more closely together on this diagram. If we take the Weyer and Osterbrock diagram, which is the same vertical axis, but here is the sulfur 2 over H alpha. This time, this is less sensitive to composite, but it's more sensitive to differentiating between Seifert-like, which is really AGN photoionized, and liner-like line ratio. Liner-like can be a faint AGN, but it can also be shocks. And then if we now color code to this, what we see is that AGN, well, the photoionization cone remain strongly and basically purely AGN photoionized. It's all Seifert-like here. However, to me, it's very interesting to see that there's this region kind of just outside the cone that may be consistent with like more shock ionization, which if we imagine this gas coming out as an outflow, it's easy to imagine that maybe this outflow is pushing on the other medium and that medium can become shocked. So this is a bit more speculative in terms of the shocks, but we're very confident that the outflow is AGN photoionized. So we found ionized gas outflow. We found that these outflows are AGN photoionized. It's still not fully 100% whether the starbursting is contributing to the outflow, because one could maybe imagine that the starbursts are launching the outflow, but then the AGN is radiating. I think it's a bit contrived, but we still decided to look at if we can learn anything more by looking at the previously observed radio emission in this galaxy. So I'm zooming in a little bit. This square here is the size for the bottom. So this is just the radio continuum at 8.5 gigahertz. And it's elongated. This is the beam here. And so there's a bit of a, you could say an extended component, except there's some, in the literature, there's some disagreement. So some group claim that this is radio, the extended part comes from the starburst in the ring, which this is the overlap with the stellar velocity. So this is where the ring is. And then this is the outflow of the gas, the ionized gas. And then there's others that say, no, this is actually a small radio jet. So we've been a bit thinking about both options. We tend to favor the radio jet hypothesis. But if it's a jet, it's kind of funny shape, and it would be not coming out of that ring. It would be stuck possibly in the ring or against the ring. I mean, this is again, now we're entering a little bit of the speculation domain. And there's a previous paper on the same galaxy by Ricci et al. 2018, where they used different data from JMUSE and I believe maybe X-Shooter or Symphony. Sorry, I'm not sure exactly which one, but they used different data for the same object. And they proposed that on very small scales, there's a radio jet, so using the same radio data that we're using here from the literature, that is misaligned with the torus. And that is based on putting all these pieces of the puzzle together, which is something we're also trying to do here. So it was interesting to think about this, and I'll show you in a couple slides what I'm thinking. But let's think about what a radio jet would do, and what if there is a radio jet, and if it's misaligned or it's more in the disk instead of perpendicular to the disk. So this is work, this is actually a couple of these papers. I'm only listing the year here. There's two in the same year. So where the idea was to launch a jet in a clumpy medium. Because if you launch a radio jet in a smooth medium, it behaves differently as well. So what happens if you launch a jet in a clumpy medium, which could represent some kind of a disk with a variation in the density. So these are 4 snapshots with time, increasing time. You can see the time at the top here. And this is showing the density plot. And this is the direction of the jet. So 70 degrees. So here, 90 degrees would actually be in the disk, and 0 would be up like this. So 70 degrees means it's only 20 degrees from the disk angle. So the jet starts to propagate, but it quickly hits these dense clouds, and it starts making these bubbles that are going opposite to the jet. So this bubble is basically this hot diffuse material that's following the path of least resistance. So it's traveling between the clumps. So you end up making, it's not quite a sphere, but you end up generating these big bubbles because the disk, the jet is so inclined and it's going against the disk basically, and with a clumpy medium. So this was very interesting because if we think of the scenario that, so I'm just using 2 of the snapshots here from before, and I tried to rotate them and scale them to be a similar size as what we have in the observation here. So this looks like, you can see the little radio jet in dark blue in the center here, and then these bubbles of outflowing gas here. So what does not match is the timing. So these simulations are 90,000 years and 180,000 years after the jet is launched. We calculate from radio data, from the literature, additional to this to get some radio index, a range that if it's a jet, it would be quite a young jet. So the timing might not be quite right, but we see some very similar, at least tentative, intriguing possibility for this scenario. So one possibility is perhaps we have a jet misaligned, like it was proposed by Ricci et al. But I want to say that the jet is stuck inside a bigger ring. So instead of this being a torus, this could be this big ring that's about 600 parsec across. And we see the outflow coming out of the ring. So again, this is just a possible scenario to be confirmed with more data. But I just recently found this work by Venturi et al. That I was very interested in, because to me it was a bit striking, the similarity. So sorry, just to start again. So this is NGC 5643. And this is the O3 emission line in the region with this yellow square here. So this clearly this elongated O3. So the color is O3. The contours is radio. So there's also a radio jet that's quite well aligned with O3. The O3 emission line shows harder to see, but there's a blue shifted and a red shifted component. So there's again a biconical outflow here, but this time the radio jet is in line with it. And what's interesting is if you look at the width of the O3 emission line, so not the flux, but the width, it's actually enhanced perpendicular to the cone here and perpendicular to the radio jet. So the interpretation here is that there is a regular AGN outflow, but the jet and or photoionized outflows are causing shock by expanding like this. It's also pushing against the material in the galaxy, and that's what is becoming shocked. So that's the possible scenario here. But to test for shocks, the authors here use the same diagnostic I showed you with the S2 emission line, which is a bit better at distinguishing between AGN and liner-like. And you can see clearly here this liner-like emission and this Seifert-like. This is even more clear than in the 7582 I was showing you before. So what is to note about this work? So they have a sample of a few galaxies, and they all share the same property of having a low power radio jet. So nothing like the very big obvious ones with the big low. So a low power small jet. And this jet is highly inclined. So it's within the disk, within 45 degrees of the disk itself. So I find this very intriguing as a possibility. So I'm summarized this part here. So we have confirmed these O3 ionized cones that are outflowing. The agent photoionized the cones themselves. There might be some shocks around them. We found the KDC, so it's a 600 parsec ring. And it seems that this galaxy substructure, so this ring, actually that plays a role in collimating the outflow. So this is what we're proposing. And it also contributes to agent obscuration, which I didn't talk about here, but we calculated how much it contributes. And it's 10 times more important than the dust lanes. It's not what makes it Compton thick sometimes. This is really happening on smaller scales within the torus, but it's an important contribution. So 10 to the 23, atom per centimeter square. Okay, so we still have some open questions. And I want to say that to go from one case study to the bigger picture, if you really want to understand AGN feedback, I think what we need to do is to combine a lot more of spatial result studies, but also large galaxy surveys. So this is an incomplete list here, and some of you on the call are involved in this kind of work. And also I would like to throw the invitation to please send me your favorite papers. I've not been fully up to date in the last pandemic years. And also I apologize if this is not complete, I ran out of time. But I'm very interested, and to me, it's super exciting to see all this work coming up, and including some of these being larger surveys too. So there's more like small detailed surveys and then larger surveys, but less detailed. So this, typically a compromise. And for large galaxy survey, I'm gonna use the next few minutes to talk about the dark energy spectroscopy instrument, because I'm very involved in this project. So that's installed here and working right now in Arizona at Kitt Peak. It's on the 4-meter Mail telescope. And then these are references to look about the science and survey design and the instrument design. What is very exciting about this is that we're gonna have spectra for over 35 million galaxies and quasars over the course of 5 years. So there's also photometry to go with this, because the DESI targets for spectroscopy are all selected from imaging. And the imaging is actually a combination of ground-based GRZ band imaging again, from wide field cameras on mostly 4-meter telescopes, but also using the WISE satellite and WISE 1 through WISE 4. So this is infrared imaging. And the nice thing is WISE 1 and WISE 2 are going quite deep because after the primary WISE mission was finished and resulting in the all-WISE survey and catalog, there was the extension called NeoWISE has added more than 6 years in these 2 bands. So this is going much deeper. But in addition to this, the way the photometry has been done for the DESI project is to use a forward modeling approach using the tractor algorithm. And this has forced photometry, so it will help to deblend. So WISE has a much bigger PSF, so the sources are more confused, but we use a ground-based GRZ to help deblend the WISE. And to show how much we can gain with this, the all-WISE catalog, this is the number of sources as a function of WISE 1 magnitude. So from bright magnitude here to fainter magnitude, this is what you find in the all-WISE catalog. And then this is what we get with the tractor force photometry. So we can go much fainter for a lot of galaxies and AGN, which is what we're interested in. So DESI is exciting because, as I already mentioned, it's going to be 35 million redshift for galaxies and quasars, also 10 million spectra of stars. And their galaxies are split. So there's a bright galaxy survey at low redshift, and then which will be about 10 million of them. So think about SDSS, but going out to redshift 0.4.5 instead of redshift 0.1-ish. And then the luminous red galaxies go out to redshift about 1.1. And then ELG are emission line galaxies, mostly using O2 because the doublet is well resolved with DESI. And this goes out to redshift about 1.6, 1.7. And then quasars extending out to redshift 3.5. So this will create the largest ever 3D map of the universe with the redshift information, which is exciting. But I'm mostly interested myself for the spectra and galaxies and AGN. The redshifts are coming really fast. So DESI actually has 5,000 fibers. So one observation over, let's say, 15, 20 minutes gives you 5,000 spectra, including sky and other things like this. But still with this high multiplex, we can get on average 50,000 redshift per night. And this one night, which was the record holder with 100,000 redshift in one night. And on May 4th, with just the survey validation, we already crossed 1 million good redshift, so with good quality. There's a concept of redshift by breakfast. So the night of observation happens, and then at NERSC at UC Berkeley, they have the pipeline running. And by the time you're drinking your coffee and having breakfast, you can look at the redshift of the night before. And these are the redshift distributions in these 4 different target classes for this. So I'm very interested in finding AGN also from the emission lines and looking at not only the line ratio, but the line profiles. And I think lots of people are also interested in that because line profiles can tell us about the kinematics. So when we don't have integral field, especially resolved, so we don't have a map per se, but we can at least identify interesting objects, because if the line kinematic has a big blue shifted broad component, let's say on O3, we can say, whoa, this is a candidate to have an AGN outflow. So what I'm doing here is this slide is I put together just a list of possible AGN science highlights without going into details. This is to also inspire you, hopefully. So there's 2 different classes of quasars. So tracer quasars that are just tracing the structure by their clustering and so on, up to redshift 2.1. And quasars that are redshift above 2.1 to 3.5 start to have Lyman alpha in the window. So then we can also use them as probes of the forest. So these actually get observed deeper than the main, than the regular quasar. But in addition to these big quasar samples, there's also going to be some high redshift quasars. So people are trying to find candidates and already pushing to higher and higher redshift to understand really the early growth of black holes, because black holes have to go really fast, really soon, really early. But also looking, for example, at red quasars that might miss regular surveys, but what are they, why are they so red? why, you know, there's like a lot of interesting questions there, because does it correspond to a particular phase of galaxy evolution? And also changing look quasars. So there's been a lot of studies already done on this, including some systematic searches, which we could do now because a lot of quasars that have already been observed with SDSS BOSS and EBOSS and so on will be observed again with DESI. So we can use this time difference to see if there's any changes in those. In addition to looking at AGN that are maybe not quasars, so going to lower luminosities. And again, a lot of options there. So looking at type 1, type 2, which can tell us about the torus, looking at population studies, so luminosity functions, how the AGN properties and host galaxy properties depend on each other, looking at line profiles. So DESI is actually nice because it has a higher spectral resolution compared to SDSS, so we can get finer measurement of the profiles. And also because it's the parent photometry is about 1.5 magnitude deeper, we can search for AGN and low mass galaxies, which I think Shobita here on the call would be interested in. Okay, so this is a preliminary look. So Raga Deepika Pucha is a graduate student at the University of Arizona, working with Arjun Day and myself mostly. And she joined the DESI project and started already taking a look at the early data from survey validation. So this is all preliminary. But just having a quick test was to look at the BPT shown here in the 4 panels are 4 different target classes. So one thing to note, which the survey validation data are actually a bit more loosely selected because the purpose is to test a target selection. So people expanded their selection criteria. So we get kind of a broader range of possible targets, which actually turns out by chance to be very interesting because these that are supposed to be emission line galaxies at higher redshift and QSOs that are on a galaxy side, they basically are just galaxies, mostly. So they basically have colors that made them look like QSO, made them look like ELG, but they turn out to be these galaxies that are less luminous and lower mass than the main sensitivity of the low redshift survey. So this is the absolute magnitude in Z band, which correlates quite tightly with stellar mass. So we will repeat this with actual stellar masses in the future. But for now, this red line is roughly 10 to the 9.5 solar masses. So below this would be a low mass galaxy candidate. And the Bright Galaxy Survey and LRG are actually more massive system. And these accidental ELG and QSO gives us this nice population of low mass galaxies to study. So Raga is very interested in trying to also find these AGN and low mass galaxies. So previous work from SDSS, for example, Amy Rines and our group came up with a sample of low mass galaxies that have an AGN from SDSS. And Ragas checked if by chance we had any overlap. And it turns out only 2 objects for now in the first data. But this is fun to compare them side by side or top and bottom here. So this is the DESI spectrum and the SDSS spectrum for the same object, and the DESI imaging and SDSS imaging for the same object as well. So they're quite similar. What I find could be an advantage. Again, this is kind of a minor difference. I think other spectra are more different. But with a higher resolution, I think it will help to de-blend the lines that get a bit blended. So we can already, of course, resolve a broad component H alpha already with SDSS. But to better de-blend like the N2 the other doublet and the narrow H alpha from broad H alpha, I think having this will be an advantage here. Okay, so another possible AGN science case is to look for double peak emission lines and what that means. So this can help to find dual AGN, but it could also be tracing kinematics, such as outflows or the narrow line region. So it's not like a one physical interpretation, but it could make a nice sample to start from and then follow up to find more information. So what I'm showing here, so this was not a SDSS target. This is what it looks like in SDSS at the bottom, but it was a DESI target. And then this is the region around H alpha, N2, and S2, and they all show this kind of similar double peak. And this is another example. So these were found by not even trying, not looking for them. This is trying to just look at a few randomly selected AGN and just noticing them by chance. But I think a systematic search would be very nice. So the survey validation has been done now for almost a month, for over a month even. And that led over 1 million redshifts and 400,000 stars. And the official survey began on May 17th. And there's already over 1 million redshift in the survey. But the SV data, this part, will be publicly available. So this is also why I want to show you all this exciting science, because in early 2022, when it's publicly, everyone is welcome to jump in and have fun with this data. So I made this very simplistic, simplified conclusion, but let's still hopefully have some discussion. I think we have made a lot of progress, like as a community, to understand AGN outflows. There's still open questions, I would say, regarding the impact of those outflows and what we call the real AGN feedback. With DESI, we should have over 5 million, I think, AGN to understand the connection with galaxies, in addition to 2.4 million quasars that are higher redshift. So I think there's lots of opportunities with DESI spectra themselves, but also there's already WISE, and some regions have X-ray and other multiple event data. But also with such a big, large sample, we can do find interesting outliers and then follow them up with detailed studies. So I went a bit over time, but I'll stop here.
Thank you so much, Stephanie. That was very exciting, and what a nice combination of a very detailed project with an overview of DESI. I want to encourage a lot of questions, and we're hoping to make this more of a discussion. And if you want to share about your own projects, you're welcome to do that too. If you want to get Stephanie's wisdom on them, if you want to, you know, talk about potential ways to follow up on her research, that would be great too. And also I want to encourage the students who were meeting. We had a separate meeting yesterday with a few of our students, and a lot of the questions that they asked during that meeting were actually answered by Stephanie right now. So it's great. So if you want to ask any follow-up questions, I'd like to encourage that. Mike Crenshaw.
Hi, Stephanie. First of all, it was a great talk and beautiful data. So I had a question about the BPT maps for NGC 7582.
Let me go back to this to help with the, oops. Okay, I think what happened is oh, there you go. The BPT for the BPT map, there it is. Okay, let me start sharing again. Okay.
Yeah, so you had mentioned that along the edges of the bicone, you see this sort of liner-like ionization. And you know, this looks like sort of an orange color here in that right there. And I think you'd mentioned the possibility of shocks. I don't think I heard you mention the possibility that it could be just like the same phenomena that we experienced with liners, which is that there's something upstream, something that's absorbing out the ionizing flux, or a big part of it, and therefore you get the lower ionization gas. So there's some papers out there, for example, by Steve Kramer and others, who are able to model the edges of the cone and show that all you need is some ionized gas clouds along the edges closer in to give you something like that.
That's very interesting. Would you mind to send me those references?
Absolutely. In fact, I can try to put it in the chat here. So
okay. Yeah, I think this is the part where this work was not fully quite conclusive. We were just exploring options. So our strongest conclusion is that the AGN outflow itself, we think is AGN photoionized, but we had more of a question mark about what's going on with this liner emission. So I would be happy to look at the references and consider this in the discussion.
I sent you one. You could probably go from there. Thanks. It was great talk again.
Thank you.
Okay, Bina was next.
Hi, yes. Very nice talk, and I love the results and very beautiful figures. I just have a couple of questions about the same target and just 7582. Have you looked at the mass outflow rates in this object? And so that's one question. And have you looked at the effect of the outflow? I know you said there's a lot of more work to be done, but essentially, is there an effect on evacuating the gas from the gas reservoir or anything in this particular object?
Yeah, those are great questions. And I will admit now I have not computed the mass outflow rate, and I've also not looked. So basically for your second part of your question about the impact, we could calculate whether this gas is likely to be fast enough to leave the galaxy, or whether it will simply slow down and kind of rain back on, like maybe a fountain. So I have also not made that calculation, so I'm not sure. The original idea was that this paper would be closer to the observation, and then there would be a follow-up that would do more of maybe of the modeling, because we need to take into account, so the velocities are showed were projected velocities, so we need to take into account the inclination and the angle to properly do it like in 3D. So this is not yet done, but those are very great questions, and that would be very interesting.
So you don't have a kinematic model for this?
Not yet.
Okay. Thank you.
Thanks for the great questions.
Sebastian? I'm sorry if I said your name wrong.
No, that's perfect. So thanks, Stephanie, for a wonderful talk. I just wanted to ask you, on one of the galaxies you mentioned, it's type 2 in optical and type 1 in infrared. So you mentioned about the galactic dust lanes, which could be the reason. So what are the column densities typically for these dust lanes?
Yeah, so the larger scale dust lanes are actually not that high column densities. They're more like 10 to the 22. But that smaller region where we think there's a ring, that's 10 to the 23 in terms of column density.
What is the distance? I mean,
at the distance?
Smaller and the larger regions. So
yeah, so we think it's about a 600 parsec diameter ring. And I'm not sure what's the opening inside the ring. So I don't know how thick the ring is. I mean, we have a column density, I guess, but then and maybe an upper limit to the size, but that still doesn't tell us and how clumpy it is. So it's, and there is evidence for very high column density, like closer to 10 to the 24 on very small scales. So that would be like within the torus, like within the dust sublimation radius scale as well. So this would be gas. Okay.
So great. So why I'm asking this, because I mean, Matt Malkan has a very seminal work in 1998 with HST, and so we published a paper last year on X-ray obscurations of Compton thin type 2 galaxies. We found that indeed, like clumpy torus and inhomogeneous medium in few hundreds of parsec scales, and also like the galactic dust lanes could be, I mean, a combination of all of these could be responsible for obscurations in the X-rays. So since you measure about, I mean, you mentioned about these 600 parsec scales, dust lanes of Compton, I mean, Compton thin, but it's kind of quite high, I mean, compared to normal galaxy dust lanes, like which are like less than 10 to 21 or less than 22. So this is very interesting. I mean, it's corroboration of what we have also found in X-rays. Not spatially resolved, but it's in some spectroscopy, yeah.
Yeah, I think it points to, I guess sometimes people say multi-scale absorbers. So they could be absorbers on small, medium, and large scale. So I would consider this ring kind of a medium scale. Absolutely. I guess it's a circumnuclear scale. So it's not galaxy, but it's not also nuclear.
Absolutely, absolutely. So we, why I asked this question also, like the distance scales are important because in X-rays, the variability time scales also, like if we just relate it to the distance, we found that indeed there are like tens of parsecs to hundreds of parsec scales distance, like days to months time scales variability. So indeed, I mean, they are not nuclear either or not the galaxy scales. There's something in between. So yes, great.
I'm gonna put my email in the chat because if you would also like to send me references.
Absolutely,
Oh,
yes.
sorry,
Yep.
it's not capital S. I just did that by autocorrect. Yeah, so thank you. This is very interesting.
Okay, perfect.
Sharita?
Oh, Gabby, don't choose me yet. I can be last because I want to give everyone a chance.
Okay, Thomas.
Hi, Stephanie. Very informative talk. Thank you. So my question is with regards, so you mentioned that in the near infrared, this target appears as a type 1. And I was curious if any of those studies in the near infrared have looked at the outflows. If there's any,
Yeah, so that reference here, this paper by Richero, they also combine, I think they mostly use publicly available data, but they combine lots of infrared data, including high resolution also from VLT. So, but I did not mention this in this talk, but I should have. In this paper and also elsewhere, sometimes if we look at H alpha in detail, we can see a broad component at the base of it. So there is a broad component in optical, but it's so faint. And it's, if you have like a spectrum of the galaxy, it's completely missed, like it's swamped. But if you have IFU and you zoom in the central spexel and you take the spectrum there, we can also see the broad H alpha. And we can also see it with MUSE, but it was first reported maybe in this other paper. So I think the fact that it is a broad H alpha that's been seen sometimes, either it means that it's so dusty because there's a foreground screen of dust that we mostly miss it, or it could be changing look, that sometimes it's type 1, sometimes type 2. I'm not 100% sure of the full answer there, but it seems, yeah, I think it seems that to me, I would say it's more likely to be a type 1 that has this extra dust in front of it.
And so did this group also look at the kinematics of the outflow in the infrared?
I'm not sure.
Or I guess has that been looked at in this target? It would just be interesting to see if the outflow appears in the infrared and how it compares to the optical.
Yeah.
Yeah.
I think the infrared IFU data is a much smaller field of view, so we don't see the as large scale. So this O3 outflow is quite large scale. It's a several kiloparsec. Well, a couple of kiloparsec.
Okay, well, thank you.
Louis?
Yes, hi, Stephanie, great talk. Regarding this object, is there any maybe follow-up observations, maybe using higher resolution radio, some type of VLBI, to maybe see if this jet is in fact misaligned?
Not yet, but if you volunteer to help, I've been thinking that this is I've been discussing, it's hard to, I think it's really hard to observe this object from the VLA, and because it's so far south, -42 deck. But from, I think it was ATCA maybe in Australia, where we could get at least different frequencies and get the, yeah, so, okay. The answer is, not that I'm aware of, we don't have higher resolution radio. I think what we would need to have is higher resolution radio at least different frequencies to look if the radio spectral index remain like jet-like. So not just in the center, but also in the extended portion. And I think the issue is I'm not a radio astronomer expert, so I will welcome help in that field.
Thank you very much.
So before we go to Shobita, I'm going to put Matt on the spot because he's unmuted himself several times.
Well, both of the talks are great. I really love it. This maybe is not the most perfect illustration of your O3 cone here. I think the first one you showed was just knocked me out so much that the southern edge of that cone is so sharp and so straight, it's like a knife. Now, people have shown one or two cases of this before. They've commented on this, how do you get something collimated so beautifully like that? There are a few physical explanations that could do it. Do you want to speculate? But maybe the previous slide was even more dramatic. No, oh yeah, maybe slide 16 showed it pretty good.
Oh, well, slide 16 is
no, oh, sorry, no, that shows the inner part. No, it was an earlier slide where, I'm sorry, I forgot which one it was, where, how about slide
with
slide
the
15?
kinematics, perhaps. It's not here, because here we also see it in
Well,
the
that's pretty, that
kinematics.
shows it fairly nice too. Yeah,
And also this is
that
the
one right there. Look how short, and it goes on beyond that kiloparsec bar there. Yeah, I mean, I was just amazed at how straight it was.
And if we look, I didn't show it here, but if we look at the gas width and we don't decompose it, so we say how big is the line, the cone actually goes right away. It fills the full MUSE field of view, and it's like this, perfectly like two edges like this. And it's the same on the other side.
Yeah, it's huge, and it's a very wide opening angle, like 90 degrees, but still a sharp edge. It's fascinating.
Yeah, and I didn't talk too much about this, but I think it's also a bit more hollow in the center.
Mm-hmm. That's very interesting. Yeah, kind of looks like it, doesn't it?
So we talk about this a bit in the paper, that it seems to be not necessarily fully hollow, but at least more diffuse in the center. So, which to me, in my mental image, I'm imagining an outflow which is going out, but also outward, but also outward the other way. So it's like just the fact of having, well, I guess there's different ways to imagine it. If you think if it's something that would that is launched in all direction, and then you put a ring around this, so then the collimation is really from that ring, because it can't go in all direction, because then it hits the ring. So that's forced by the ring. But the other thing is, if you have something that's more launched like a jet, but it encounters resistance, if it encounters resistance, it will open like this. And I don't know between these two scenarios, which one will make it hollow in the center and more filled in the edge. But that's a great question. I think understanding the physics is always the most exciting, even if it's not always the easiest part.
And when you're saying collimated by a structure, you can call it a torus if you want. You mean it's physically collimated? That's one possibility. So there's a wall, and gas just can go on one side, but it can't go the other side. Or do you mean that the ionizing photons are blocked? There's two kinds of collimation, right? One is blocking the motion, the other is blocking the photons.
I agree with you. So my own scenario that I think maybe I'm the only one on the author list to support is, because it's type 1, I'm thinking if there's a torus, the outflow is coming toward us, but we don't see it toward us because there's this ring. So I think it's bouncing in the ring and going sideways. So now to prove it is another another question. But if I try to imagine what's going on and I look at all this data and I look at the fact that I think it's a type 1, I'm thinking that this ring, okay, and also another interesting scenario for having an inner wall, because if you want to collimate this way, if the material is bouncing and being deflected, you need to have some kind of pretty dense structure. So one possibility is that this ring started as a disk and the jet is carving a hole in the middle. And then, which to me would make a pile up on the inner radius of the ring. And I think it could do this. But again, to prove it, I think probably would require either a dedicated simulation or what could also help is to get much higher resolution view of this. Because right now, I don't think we can conclusively say if the outflow is coming from within the ring or from the ring itself, also a little bit. So I think higher resolution or dedicated simulation is probably what we need.
Sounds good.
And the higher radio also, resolution.
I just wanted to ask you to clarify, when you talk about a ring, are you talking about a ring of just dense material, or what kind of ring?
So it would have to have stars, molecular gas in it. So it would be and dusty. So it would be a dusty, gas-rich ring that's big enough to also host starbursts within the ring.
I see. Thank you.
So a substantial structure.
Okay. Francisco?
All right. Yes. Hello.
Yeah, we can hear you.
Okay. Hi. Hi, Stephanie. It was a very nice talk, and the MUSE data is amazing. I just wanted to add something. There was a question about the near infrared data, and we have observed this galaxy with Symphony, and I have the data. So if you want, we can share some images, or I can give you some of the maps that we have extracted for this galaxy, as well as the spectra. And that's something I also want to mention, is that this galaxy sometimes, well, in our data, actually, there is a broad component of bracket gamma.
Yeah.
Yeah.
Yeah,
So,
I think I'm mentioning this in the paper, the broad bracket gamma, as evidence that it's type 1 in infrared.
yes. Yeah.
Yeah.
So if you would like to collaborate with the Symphony data that we have, yeah, just let me know. Yeah.
Oh, that's exciting. Okay, I'll be in touch.
Mm-hmm.
Great. Erin?
Yeah, I'll just follow up on what Francisco has said. This is really amazing MUSE data to see, and it's nice to see how this can fit with our Symphony data. Also add that we have ALMA data, as you mentioned on one of the slides, you included ALMA data's paper on this, and we're beginning to do some modeling comparing the cold gas that we're measuring with ALMA and then that near infrared molecular gas. So you had mentioned constraining that disk geometry. That's what I've been spending my last week or so on, and this is one of the galaxies in that sample. So I'd be happy to share that with you when you get to that point. I'd be interested to compare what we're seeing on the smaller scales within that central kiloparsecs against what you're finding using the larger scale data as well. But yeah, I think that Symphony data could help, as well as the ALMA data, figure out what that outflow structure really looks like. So it'd be fun to collaborate on that.
Yeah, this is super exciting. Thank you. Okay, so I'll also be in touch.
I know, I'm getting excited too.
Yeah.
Louis,
Everyone can join the
Louis, is your hand still up from before, or do you have a new question?
I'm sorry, I forgot to put it down.
No problem. All right, I think Shavita is finally your turn.
Yeah, so I just, first of all, Stephanie, that was fantastic. It got me really excited. You know, both from the intricate, you know, small scale studies that you can do with 3D spectroscopy, and then this amazing large survey that is soon going to be publicly available. So thanks so much for that talk. And I should just say that I don't want to keep people, you know, this was meant to be an informal sort of gathering to brainstorm, and I'm sort of going to ask more general sort of questions or ideas based on this amazing data. But first I want to ask a very specific question, which is, just read the paper on Circinus about the MUSE data, where I was really surprised that they showed corona line detections all the way out to 700 parsecs. So, you know, just suggesting that it's not photoionized. And I wanted to know if you saw any faint corona lines in this data set, and does that sort of make us rethink whether this is really photoionized by the AGN? And I guess the fundamental question of, you know, how much is the AGN and how much is star formation contributing to the outflows, I started thinking a lot more about, and there are a lot of experts here. So Aaron, Francisco, Matt, just wondered what your thoughts, and Stephanie, what you think about that.
Yeah, so I did not specifically look for coronal lines. I think there's some, at least in the central nuclear region, for sure. But I didn't look at how the spatial spread. So I mentioned at the beginning that this galaxy and others are also part of the S7 survey, which was led by MAGNUM. And I think he specifically looked at the coronal lines in one of the papers in that survey for a few objects. So the S7 data, they have worse spatial resolution. They only resolve like 2 or 3 arcsecond, but they have very high spectral resolution. So they pick out all these small lines. So there's amazing nuclear spectra from there. So I guess I'm afraid I don't have the answer to your question specifically for this one. And in terms of outflow coming and the ionization and the launch of the outflow coming from starburst versus AGN, I guess it's been an open question for a long time, but yeah, maybe I'll let the chance to others to speak, because I've also seen, I think this papers where these outflows that were identified with this outflow is from the starburst, this outflow is from the AGN. Like for example, I think David Rupke, but I think maybe Francisco also. So maybe I'll let somebody else comment on this about finding like multiple outflows in the same object.
Yeah, Sharita. So I have looked to the near infrared spectrum of this galaxy. We haven't really analyzed this galaxy, but there are coronal lines, specifically silicon-6. Yeah, so I don't know how extended it is. As I said, I just look at the spectrum. It's like, I also know there is a broad bracket gamma. But yeah, we haven't looked at the data yet.
Oh, that would be exciting.
Mm-hmm.
I can add quickly that looking just as you were going through your talk, I was pulling up the maps that I have just to see how they compare. And there's some interesting velocity structures in the silicon-6 line that it's extended out to the symphony field of view, not uniformly, but there are some patches of, there's definitely some structure there that's of interest to compare and consider in terms of modeling of the outflow.
Great,
and I should add actually, if from that paper here, yeah, totally forgot, sorry. These they're comparing also shock indicator. They have some like iron line. I'm trying to remember now, but I don't have the, kind of have a mental image, but I would recommend to look at this because they found that along the starburst, there seemed to be shock region as well. So, but that's perpendicular to the outflow, but extended, which could potentially be that the ring has shocks inside the ring or even reaching out. Anyway, I think this deserves a bit more conversation. And yeah, sorry. I wanted to mention, I think Aaron and Francisco and Shrubita, you might all be interested to see what they have in there too for the maps.
Exciting.
I was wondering if Vivian had any thoughts on your question, Shrubita. Now I'm putting Vivian.
Yeah, I didn't see Vivian is here too.
Yeah, sorry, I was hiding.
Oh, there you are.
Yeah, no, in terms of like seeing the starburst, I think I'm interested in actually looking at like based on what Francisco and Aaron are talking about in terms of their symphony data and the infrared. But I think if you see some kind of starbursty rings, and maybe you can calculate some sort of star formation rate and actually calculate the and you mentioned that the star formation rate is actually comparable to the mass outflow rate, right? And so I think it'll be interesting to look at the energetics from that standpoint, and just like seeing where where things are versus how much things are. But I don't know, like this kind of comes back to like this really nice data, and then I'm really interested in like the high resolution sort of data to really see where things are lining up. So, you know, part of it, you know, Stephanie, I was excited about this data set even when you presented this at UCI a couple of months ago. And so, you know, I think it's just amazing to see what other properties you can measure from those data sets. But.
Yeah, so definitely, I think you're right. I agree with higher resolution would be super nice, but also measuring the star formation rate in the ring compared to the mass outflow rate would be interesting. When I quoted it before, this was for the simulation, that they were comparable. I did not actually measure them for the observation yet, but that's just a great one. Like one of these things is the MUSE data. There's so much information that I feel like the paper would end up being a textbook. So I was trying to cut it and have more of the physical modeling in a separate effort, like a follow-up. But this would be basically like on top of the list, right? Like we would have to check, maybe can we calculate AGN luminosity, what the luminosity is from the outflow itself, what's the mass outflow rate, what's the star formation rate in the ring, right? All these things I think would be very nice to help with the physical interpretation.
Definitely. And I think, you know, when I was listening to you, I was thinking about an object that I was working on where we have some high resolution ALMA data, and we do have like some spectral indices, you know, within band 6, and we actually saw in one of the galaxies, so we think it's a starburst galaxy, but there's hints potentially of you know, a very compact core. And there's also, when we look at the spectral indices, the central clump is actually a very negative spectral index. And, you know, the synchrotron jets, is it actually driving, you know, the outflows we see, or is it, you know, due to something else? And, you know, we're not really sure. And so, you know, like, you know, I was kind of supporting, you know, Lou's question earlier about whether or not this would be really interesting to see, you know, further explored in radio and submillimeter when you have that spectral index map to compare to.
Great. Onik?
Yes, I think I have a similar question to already people asked a lot of questions, so I already have a lot of answers. I just want to know, like, yeah, we are doing some VLV observations of some AGNs, and we already see some smaller and weak jets coming out in different frequency in the radio band. But my question is, what actually going on the hollow region of the biconical outflows there? Like, is there any star formation going on, or like any that misaligned jet is making any bubble inside the hollow? So what's physically going on the hollow region of the biconical outflows? That is my question.
So is this, I hope this is a question for the group because I don't have the answer. So you're asking if like the physical reason why the cone would be hollow, a bit like in the
like, I mean, is that because you also say the mass of the outflows is comparable to the star formation rate? So is there any possibility that?
So I did not calculate for this galaxy, so I'm not sure here what's the case.
Yeah, I'm just thinking like what is going on the hollow region there? Like there is any making any positive feedback to create more stars, or like is there the hollow region is because of the bubble creating by the misaligned jet? You know, like what is that region doing physically? That was my question basically. Yeah,
right. So this kind of adds things to calculate, right? Is there enough power in a jet to make a bubble? If this looks like a hollow cone because it's in fact bubbles, but we don't see like the end of the bubble, right? So that's a way to make it denser on the outside and diffuse in the middle. We would need to check what's the power of the radio jet and how much is needed to power a bubble, and
in the hollow region.
Also, yeah, properly, you have to kind of go back in time and how long it took for the bubble to reach that size. So assumptions needed, but so I'm not sure if we can say, and I think this is related to your question, but can we say, is it possible that this is a radio jet that powered the bubble, or does it have to be disk winds from the accretion disk? And can we distinguish? Right? I think this is kind of
That'll be interesting, yes.
yeah. So I'm not sure what's the answer, but I think this is kind of the direction that we should be going with the more
Yeah,
physical
like the
modeling.
yes, and the high resolution radio observation could be
Yeah.
useful there. Yep.
It would help to at least calculate the probability that the radio jet can be the cause of the outflow. I think for the disk wind, I guess there's X-ray data. We can estimate some kind of accretion rate and compare with the O3 luminosity maybe, but it's very dusty in the center, so we don't really get the central O3, we just get it from the cone. So that.
Yeah, yeah, because especially one image, I think 18 slide number, you showed that there's in the hollow region there is some I think bright spots as well. So I thought like not the
yeah. Let me see. So the
yeah,
thing
this one
is,
here.
this is of course this is a 2D projection of a 3D structure, right? So we only have the line of sight velocity, so it's hard from just from the velocity, but from the flux, there's definitely some entrained material, and I don't know whether that material is inside the cone or like on the edge part.
That's true. Yeah. Thank you so much. It was a great talk and enjoyed thoroughly. It's beautiful.
Thanks.
Great.
Let's go. Guys, is your hand from before, or do you have a new question?
Yeah, Shabita and Francisco, new questions?
Well, I just wanted to, Francisco.
No, fine, fine, go on.
Oh, I just wanted to get people excited about the future, just a few words, because this is, the spatial resolution is what, 0.7 arc seconds, or? So this is like tens of parsecs spatial.
Yeah, this is being limited here, so more like 1 arc second in this particular data set.
Okay.
I mean, I was already thinking MUSE AO could be already interesting, except this galaxy was not possible to do this because we don't have a bright point source for the AO and the center. Sometimes the AGN can be used itself as the point source, but this one is so obscured that we don't get that. But anyway, so I think, yeah, you can continue your arguments, but this is about 1 arc second resolution.
But I think that most of the things looked at by MUSE and Aaron and Francisco, the Kona survey, it's tens of parsecs, right, is the spatial resolution. So with the ORCAS, which by the way, the report just went out yesterday, we can do so much better than that. So it would be like less than a parsec spatial resolution. And the question is, what do you think? Taro isn't here, but based on the, I think he said 3 milliarc second spatial resolution with VLT gravity, he did say that they detected the coronal line, if you remember in the last week's talk. So I just was wondering, what mysteries can be unlocked by going to the smaller and smaller spatial scales. It still wasn't clear to me, behind.
I think it will help a lot with these questions of what is coming from starburst, what is coming from AGN, because they're so close together, right? In this, if you have a nuclear starburst, you're basically embedding your AGN into a starburst. And so then you don't have a choice to go for, but then it's dusty, right? Also, so you need high resolution, but also to be able to see a bit through the dust. So I'm not sure exactly like all the best combo, but to me, or you could say to really separate the AGN and the starbursts themselves, we need the high resolution, but maybe it's also beneficial to have the high resolution of the shape of the outflow. So Matt was bringing up how there's like a sharp edge.
Yeah.
But is there another sharp edge? Is there like a substructure? And also, can we do the opening angle? Can we see the shape of the base of the outflow like in detail? Right now, the base of the outflow is quite broad. So I think it could be coming from this big ring that's collimating it perhaps. but it's a guess at the moment. It's like consistent, but if we maybe if we could see the exact shape of the outflow outline, it could be more of a clue.
Yeah, I agree with that. And I think this is a question that comes over and over again, right? Like we see outflows, we see that they're ionized by the AGN, but the question people keep asking is that are they launched by star formation processes and just illuminated by the AGN, right? And that's as you got the kinematics and the morphologies closer and closer to the nucleus, I think it would be a lot more, I mean, we could present a much more compelling case than, you know, now that we're sort of looking really far away from the nucleus, and then yeah, it's gas that it's moving and it is being ionized by the AGN. But does that mean the AGN launched it? I do think we would be able to get a lot closer to answering that. So this is great. I mean, we had questions for almost as long as the talk. This is fantastic. So I don't know if there's any last lingering questions or comments.
I'm going to say thank you to everyone. I'm super excited about all the suggestions and possibilities to collaborate more on this. And also thanks for sending papers. I already see a couple links in the chat, but if you want to email me, I will welcome more paper suggestions. I have to say I'm working on a few different things, so it just becomes harder and harder to keep track of the literature in all the different topics. So yeah, so I'm always happy to receive suggestions.
Well, thank you so much again, Stephanie. This was a great talk, great interaction. Thank you everyone for participating. And